Okay guys, so today we are going to talk about derivative tests that we can use to help us determine like what the shape of our graphs are. Remember that our end goal in all of this is to be able to graph a function extremely accurately. So like if you think back to Algebra 1 or Algebra 2 and you guys were graphing parabolas, at some point like it didn't really matter how steep your parabola was, right? As long as it kind of went through the points you wanted it to. But now it matters, and our derivative tests really help us get extremely accurate graphs of functions. So these notes are going to be a little longer. Please bear with me. Remember that you love me, some of you more than others, as we go through these notes, okay? So at the top of your notes, you should title it derivative tests. Those are your notes for today. So let's start by graphing a derivative, okay? I'm sorry, we're not graphing a derivative, we are graphing an actual function. And this graph is going to look something like it's going to come up, it's going to flatten out, it's going to come down, it's going to have a cusp. Okay, so there's our graph. So we need derivative tests to distinguish between what's happening at a minimum, maximum, or inflection point versus when the graph is just like leveling out. So here's what I mean. I know that like at this point, let's call it A, my derivative, so f prime of A, is going to equal 0, right? I know I have a horizontal tangent line there. I also know at this point, say B, my derivative is going to equal 0. That should be a B, not an X. Okay, and I also know that even though I don't have a derivative here, it's still a critical point. My graph is still going from, it's still at a maximum or a local maximum there. But what we need to keep in mind, and what we didn't talk about in class today, is that right here, my derivative is also 0, right? If you draw a tangent line in that region, your derivative is going to be 0. So our derivative tests help us distinguish like what's a maximum and minimum from what's just like a leveling out in our function. And that's why they're really important. So they definitely aren't things to like overlook because they matter. So the first one we're going to talk about is called the first derivative test. Whoa. First derivative test. Well, not get, that's not right. Uh-oh, how do I change it? This is a new feature in this program, I think. That's actually not true. I think I've done this before. First derivative test. There we go. Okay, so the first derivative test tells us this. Okay, I'm going to try and write this neatly. I know sometimes it's a hot mess. If your derivative, so if f prime changes sign. Do you hear my dog barking? Bella, quiet. At some point C, then there is, I'm going to kill her, a local extrema at C. Okay, so here's what that means. If we look back at this graph I have up here, at that point A, for example, in this region, my derivative is positive. Okay? However, I'm just trying to get another color. So in this region, our derivative is positive. Our graph is increasing, therefore our derivative is positive. In the other region, our derivative is negative. Okay? And the same is true at point B, right? But in this case, it's the opposite. Our derivative here is negative, and then it goes to being positive. Not equals is greater than 0. And again, if you look at that cusp, the same thing also holds true. Okay? Your derivative's still positive there, and after the cusp, it goes to negative. Okay, which is what it's saying. If your derivative changes sign, it doesn't say it has to exist at that point. It doesn't say it needs to equal 0 at that point. It's just saying your derivative is changing sign around your local extrema. So just to drive this home in even more detail, let's write that down. Okay, so if the derivative changes sign at some point C, then there is a local extrema at C. Great, so let's be really specific here. So if your derivative changes from positive to negative at that point C, then you have a maximum, okay? And that's exactly like this region right here. We're changing from positive to negative. We're at a maximum, okay? That's what's happening right here. The other is also true though, okay? So if your derivative goes from negative to positive, then you have a minimum, okay, at that point, at the point where it changes. So again, that's exactly what's happening here. Okay, we're going from negative to positive. I'm going to even make these T's in that same color. Let's see if I can erase this. Nope, I knew it was too good to be true. Okay, so it's really, really important to check, is your derivative changing sign? Is it not changing sign? Because you don't want to be stuck in the situation where you find this 0 and it's not a critical point. It's not a local minimum or local maximum. And so we always have to check this from now on. Always, always, always. Okay? So again, we're dealing with shapes of curves. And today in class, I introduced the word concavity, but I didn't really give you a formal definition of what it means, so I want to do that now. Okay, so I'm going to shrink this up. So the definition, why is it not typing? That was weird. That's an O. I don't know what that lightning bolt thing looks like, but it should be a O. Definition of concavity. I know when you're in science you deal with concavity being like convex or concave, like a spoon. I don't know, that's why I learned it at least. But in math, we don't do that. We refer to things as either concave up or concave down, which makes it easier to kind of understand. You don't really need to remember like what's the upwards one, concave or convex, right? It's either concave up or concave down. And I want to give you those definitions again. So, or not again, I want to give them to you for the first time. So we say when something is concave up on an interval, that implies that its derivative on that same interval is increasing. Okay, now think if you're in any graph, if your derivative on any graph, if you're increasing, your derivative is positive. So if the derivative is increasing, that means that the second derivative is positive, okay? And then the opposite is true for concave down. Well, actually, just in case we're unclear, concave up means like it's going up, it's opening upwards, okay? Concave down implies the opposite. It implies that your derivative is decreasing, okay? Which again, if you're decreasing on, if any graph's decreasing, its derivative is negative, so the derivative of the derivative is your second derivative, and that would be less than 0, okay? And again, in case we're unclear, concave down graphs look like that. So the reason that concavity is important, again, like if you think back to that, what I was saying earlier when I first started the video, if you think back to like algebra 1 or algebra 2 or trig or actually any class where you've had to graph anything, a lot of times like parabolas end up looking like super linear at the end, right, when students graph them. And it's not because they are linear, it's because you're not really understanding concavity. So the whole point of this activity or these notes is to really get you to the point where you can graph any function extremely accurately by using the first and second derivative. So when we put together the first derivative test with this kind of piece of the definition of concavity, it leads us to what is called the second derivative test. So I don't know why I keep shrinking this, but I kind of like it. I think it'll be cool at the end. So that means we're going to write that down next. I'm going to get a new color. I'm sick of purple and green. Ooh, pink. I like it. Okay, so our next thing is the second derivative test, and then we are going to do an example of how these two help you graph. Okay. This is pretty much actually purple. It looks more pink, and then I started writing in it. That's sad. Okay, so the second derivative test puts, again, the idea of the first derivative test together with the definition of concavity. So the second derivative test tells you two things. It tells you you have a local max at some point C if the derivative is equal to 0 and its second derivative at that point is negative. Okay, so let's think about it. At a maximum, your graph looks like that. Okay, so we're going to call that point C because that's where a maximum occurs. Bella, come here. So we are at our maximum. Our derivative is obviously equal to 0, right? We have a horizontal tangent line. And notice how our graph is concave down. When your graph is concave down, your second derivative is negative. Okay, that's what the second derivative test tells you. And then, surprisingly, probably not so surprisingly, it also works for a local minimum. So at a local minimum, so you have a local minimum at C if your derivative at that point still equals 0. But this time your second derivative is going to be positive. Okay, and we can draw a similar picture. So minimum looks something like that. Here's the point C. There's your minimum. Your derivative is equal to 0. And again, you're concave up. Okay. So those are the notes for today. We are going to use the first derivative test. Okay. This whole idea we started with the definition of concavity, finally finishing with the second derivative test in class on Thursday to really get at the idea of how to graph functions. Okay. And these tests might seem silly, but again, as silly as it is to do these tests, when you don't have your calculator and your function's crazy, you do not want to get the problem wrong because you were too lazy to check that point. Okay? Or you didn't care what the end looked like. Like, how do I know it's concave down and not just a straight line down? Or, I'm sorry, this piece is actually concave up, not concave down. So it's really important that we're doing this stuff, and I know it seems tedious and it seems silly, but when we get through doing examples, it'll start to make more and more sense. Okay, as always, let me know if you have any questions, and I will see you guys next class.